Hi everyone. Today I'd like to tell you a story. The story is called 60807. I'm Daniel Smith. I co-TL the API Machinery SIG. Been working on Kubernetes since before it was open source. So I'm LavaLamp on GitHub, original LavaLamp on Twitter. I work for Google. I'm a software engineer. I'm not speaking on behalf of Google other than they support my presence in open source. I roboed Daniel drawing my slides today. Turns out I can't draw and talk at the same time, so we're doing this in 2 steps. The story begins with a user. You won't be surprised that there's also a Kubernetes cluster in this story. And every cluster needs an API server. And of particular concern in our story today is the namespace, which I'm going to draw in a big fat line. Okay. To give this namespace some sort of name, we'll call it NS2020, because this user would like to delete this namespace. So here's the action. User says delete, API server says sure. That's the technical HTTP response code. User posts to recreate, API server says no, it still exists. There's a conflict. API server is the villain. How could this happen to us? This makes the user sad and angry. How could we do this to the user? Let's talk a little bit about how resources in Kubernetes are deleted. All objects in Kubernetes are deleted the same way. So, although we're talking about a namespace right now, there's some background information about deletion that might be useful. As with much of what I'm saying, this is a simplification because there's more to it for some particular objects, but roughly speaking, all Kubernetes objects have metadata, and inside this metadata, there's 2 fields relevant to deletion. First one is deletion timestamp. If that has a non-empty value, then the deletion process has started for that resource. And there's also a list of finalizers, and the deletion is not final until all of those finalizers have been removed. Slightly confusing because the literal name of the finalizer that we care about today is Kubernetes. And this is the finalizer that is removed when the namespace object is empty. Okay, so until that is removed, the namespace is not deleted from the system. I'm leaving out some details about namespaces have special places they keep their finalizers. But roughly speaking, all objects work like this. So let's look at our scenario again. The component in Kubernetes responsible for removing this finalizer is in Controller Manager. It's the namespace lifecycle controller. Its job is to watch namespaces that have begun the deletion process, ensure that they are empty, that all the resources inside them have been deleted, and then remove that finalizer. Namespace lifecycle controller is the villain. Now, to list the resources inside of a namespace, you need to know which types of resources there are to be listed. The process of figuring that out is called discovery. And at this point, you might be asking yourself, how does discovery work? Well, I'm about to tell you. All API requests in Kubernetes have a URL path. This identifies what exactly you're making the request about. All right, and again, this is a simplification, but for our purposes, all API requests start with the word APIs. And the next thing that comes is a group, the API group. The next thing is a version, and after that is the resource. The resource is the thing that goes in the URL path. The kind is the type, right? In a type system sense. So if you make an API request and you just say APIs, if you stop there, then you get a list of group versions that API server knows about. And if you list the group, you get a list of versions that are inside that group. Right, a list of versions. And if you list a group and a version, then API server will tell you which kinds are inside that group version. And if you say more than that, then you're making an actual API request, which will do you some good, like list objects or just, something useful. So how does the API server fulfill this contract? To do that, we should talk a little bit about API server. API server is actually 3 API servers in a trench coat. The first one is the aggregator. The second one is the built-ins. It serves pods and services and stuff. And the last one is the extensions API server, more commonly known as CRDs. And if a request can't be served by the aggregator, it goes to the built-ins. If that one doesn't want it, it goes to the extensions. And if that one doesn't want it, it gets a 404, which I've conveniently drawn off the bottom of the screen for you. Now, the aggregator may know what to do with a request, and it may be for an external API server. And this means that that request must be proxied. It is not served from the same process as the Kubernetes API server. The aggregator is the villain. The canonical example is the metrics API server, which Kubernetes ships by default. Now, this means that there's various things that could go wrong. Maybe your network is not working, at least that link of your network. Or maybe the metrics API server is co-located with a process that's hogging the node. Or maybe it just has the wrong resource requirements. In any case, the aggregator needs to get the kinds from the target API server, right? Only the groups and versions are registered with the system. So if that external API server can't be reached, then there's no way for the aggregator to tell you which kinds are in the group version that you're asking about. The metrics API server is the villain. It's kind of unfortunate, but it is also unavoidable because the extension API server is the only thing that knows what it serves. The aggregator cannot know that. It would be very heavy-handed to require API authors to list that, to pre-register that with the aggregator. It also wouldn't help the problem because even if you know what kinds, if you can't actually go out and list those things, then you also can't confirm that they're deleted. If the lifecycle controller can't discover the kinds that it should be deleting, it is never certain that the namespace is empty. And if it's not certain that the namespace is empty, then it can't remove that finalizer. So whose job is it to make sure that this thing is working anyway? I think it is the job of the system administrator, the cluster administrator rather. And I think the cluster administrator should be performing this job by using some monitoring. The metrics API server is served by a regular Kubernetes pod, so it should be possible to monitor it. Another way you can monitor the overall health, and like not just the specific metrics API server, but you just run the command kubectl API resources once in a while. It does this discovery process, and it'll tell you if some group is not working. And then you can look at the API service object for that group and figure out what component is not happy. So thank you for listening to my talk and watching RoboDaniel draw these. If you think that we could do better, I'd encourage you to come help us improve our error messages or our design. Yeah, thanks. The system administrator is the villain?